usually.
Okay, so this is a question which is asking us to come up with a story that explains why two sides of a combinatorial equation are equal to each other. So it's basically asking us to double count something. So we're supposed to count something in two different ways. And because the count of a thing doesn't change when we count it in different ways, no matter how we count it, we should arrive at the same number. Okay, so let's look at the first one. Generally, for these types of questions, you can sort of get what you have to count from one of the sides of the equation. Okay, so let's start with this one. So this side looks a little bit simpler. So I'm gonna come up with a story for this side. Okay. So this side is, well, you're basically choosing k elements out of n elements and then choosing I out of k. Okay, so these two k's are the same, right? So why don't we come up with a story that uses this fact? So let's say that, there is a set of n different students, okay, and then we want to select k of them to be part of, I don't know, the k of them have to be on the school's board or something, school's student board, and then out of those k we are going to select I members who are going to be let's say senior board members. Okay, so we have senior board members here, we have board members, and then here we have our general population. Okay, so obviously this side is exactly counting this. The number of ways we can come up with the k board members is exactly n choose k, and the number of ways we can choose our I senior board members out of those k is exactly k choose I, and when we multiply them together we get the number of ways we can choose our k board members and our I senior board members. Okay, let's see why the other side is also counting the same thing. So on the other side we have n choose I. Okay, so it's suggesting that we should count it this way. So first, without selecting the k board members first, let's select the I senior board members first. Okay, so out of our population of n, we directly select the senior board members. Okay, so we're going to be left with I senior board members here, and then the rest of the population is going to become either a board member or a non-board member, right? So we have n minus I people left here, and then we have to select board members and non-board members here. Okay, how many board members are there left to select from the general population? Well, we have already chosen I of them, right? So there is k minus I board members left to pick. So there is n minus I, choose k minus I ways to select the board members out of the remaining population, and then we're basically going to be done. So in the first step, we had n choose I ways to pick the senior board members, and then out of the remaining population we have to choose k minus I non-senior board members. The remaining population was n minus I, so okay, so this way of counting gives us this value. This way of counting gives us k choose I times n choose k, so these two must be equal. Okay. Now let's go to part 2. Okay, so for part 2, this side is simpler. So why don't we construct our story using this side? So let's say that there are we have a population of m plus p people. Let's say that m of them are male and p of them are female. And then we have to select a committee of n members out of our population. Okay, and of course these n members can be male or female or any mixture. Okay, so obviously the number of ways we can do this is just m plus p choose n, right? Because we are blind to the gender of the people that we choose. Okay, now let's count it in a different way. Okay, let's say that the number of male committee members is k. Okay, now if we fix this k, then how many ways can we how many ways are there to pick a committee with this many male members? Well, obviously we have to select these k committee members out of our male population. So there is m choose k ways to do that, and then we have to select our remaining members from the female population, right? In our female population we have p different members, and then how many committee members are there left? Well, if you're selecting k male members, then we have to select n minus k female members, right? Because they have to add up to n. So the number of ways to choose female members is just it's just p choose n minus k, right? So this is exactly the number of ways to choose a committee with k male members. Okay, now how many? Okay, so now if we sum over all possible values of k, okay, k is going to be between 0 and obviously we can't have more than m male members because the population of male people in our population is m. So if we sum this over all possible values of k, we're going to get exactly the total number of committees, which is exactly this value. Now I'd like to point out something here. Even though we are summing over values of k from 0 to m, there might be cases where this k seems a little bit odd. Let me give you an example. For example, if n is less than m, then obviously we can't have more than n male members, right? But the thing is that if n is less than m, and if we pick k to be bigger than n, then n minus k is going to be negative, right? And by convention, a negative number, when you pick a negative number out of anything, the number of ways to choose that is defined to be 0. So in general, x choose y is defined to be 0 when y is less than 0 or when y is bigger than x. So both of these impossible cases are defined to be 0, right? It makes kind of sense. It kind of makes sense because there is no way you can pick more than x members out of x members, and also there is no way you can pick a negative amount out of x members. So these definitions are pretty intuitive. Okay. Now in our case, in this sum, whenever k gets bigger than n, this term becomes 0. So it doesn't matter whether you sum over such terms or not. They are just going to be 0. So that proves that these two numbers are equal to each other. So we're done.